So today we're going to talk about how we report our answers. So far we've been working these problems and working our dimension analysis, and I've said just kind of wing it, because now I'm going to teach you how you should report your answers. Because unlike in your math class where you just have numbers for random reasons and you put things in the calculator, you can get all these decimal places, okay? But in here, the amount of decimal places that you're reporting an answer to indicate something. They indicate the level of precision of a measurement. And so, in a nutshell, we cannot report answers more precise than what we measured them. But because we have the advent of calculators and we put numbers in there, it'll give us like 7 decimals, okay? And if you write down 7 decimals, you're telling the person reading your measurements that I could measure it out to 7 decimal places. And chances are you cannot, okay? For instance, when I read a graduated cylinder, there's not 7 decimal places on that graduated cylinder. But if I wrote down that my volume was 47.38953 milliliters, that would say to the measurement that they measured it to that point, and they did not. And so that's where these significant figures comes in, okay? And so before we do that, we're going to talk a little bit about precision of measurement. Because when we are measuring things, you have a level of certainty. In other words, if I have a ruler and it looks like it's 4.5, then we know it's at least 4.5. But what if it falls between the 0.5 and the 0.6? What is it actually? And so that last digit we estimate, okay? So anytime you're reading something in the lab, unless it's digital, you estimate another digit. So like if it's a balance and it says it's 14.75, don't estimate past that because it's a digital reading. But if it's a measurement that you have to decide what it is, then you have to give one more estimation. So we're going to look at a couple of different things. So we have this nail, and we're trying to measure it, and we see that we know it's a 6. If we look a little closer, there's a noise, sorry. Okay, so we're using the significant figures. We report what we know is to be certain, which is going to be 6.5 or 6.4 or 3, whatever it is, 3, sorry. So we know for sure it's at least 6.3, but that last digit is our uncertainty where we estimate, and we say, okay, it's between the 3 and the 4, so we're going to call it 6.35, okay? Paul may say, I think it's 6.34. Sophia may say, I think it's 6.36. So that's where that level of uncertainty comes in. We know for sure it's at least 6.3, right? And then we estimate that last digit, okay? And that is something that kids tend to forget to do in the lab. They go read the graduated cylinder and they go, oh, it's 15. Well, is it 15 exactly? Is it 15, So you have to give an estimation, okay? So the significant figures are indicating the precision of the measurement, okay? We include the 1 digit plus the estimated. So in this case, we have a paper clip. We know it's at least 2.3. It's done in yellow, so it's hard to see. But yeah, I don't know why they used yellow, but yeah. So it's 2.3 something. We're going to call it 2.35. Again, you may say, I think it's really 2.34. I think it's a little bit closer to the 3 than it is the middle, so you could call it that. But the 5 in that case would be your estimated or your last digit, which would be an uncertain. Okay, so here we have this one. So in that particular, the known markings are whole numbers, so we would estimate that to be 4.5. Okay, and in this one, it's in the wrong spot because the ruler's up there. Yeah, I'm not sure what happened with that. I don't know how to fix it. I tried. It's supposed to be up there. This line right here is supposed to be up there. And so those are showing you how you would measure that. So the last example that I want you to see, that it's exactly on the 3, that we don't just write down 3, we write down 3.0, because that's letting the person know it was on that line. There was no place to estimate. Okay, that 0 would still be the last uncertain digit, but it would tell us that it wasn't ambiguous in there. So we have a graduated cylinder here. We got some liquid, and where do we measure? First of all, what's that curvy thing called? Meniscus. And where do we measure? At the bottom. Unless it's mercury. Mercury has an inverted meniscus, and we measure at the top.
What?
Yeah. Because mercury, it has to do with their surface tension.
That's so cool.
Yeah, mercury liquid is it's inverted meniscus, so it's up. So you measure at the top of that one. This is not going to be good. Okay, sorry about that. I'm back. All right, so how would we read that particular meniscus? 15.0. 15.0, you are correct. But I'm going to tell you what most kids would do in the lab. They would just write down 15. Are we supposed to just write down 15? No. So Friday, we're going to be doing a density lab. And you're going to be doing the water displacement method that we talked about yesterday. So when you're reading your graduated cylinder before and after you put the metal in there, be sure that you are estimating that next digit. Okay, don't just say 15. Say 15.0 or 15.05 or whatever you think it is. Okay? Can't breathe. Breathing is hard. So we wouldn't write 15, we'd write 15.0. But what we would not do is what they're going to say next. Is that a normal number? 15.0, normal number? Don't put it in scientific notation. That was in the video. I say X that out. Don't do it in scientific notation. Keep your answers normal. Okay? You know how I say keep Austin weird? College Station is keep College Station normal. Keep your normal numbers. Keep your numbers normal, however you want to say that. Okay. So that brings us determining the number of significant figures in a digit or in a number. Okay? So first thing is all non-zero integers will always be counted as significant. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, always a significant number. Okay? The problem is your zeros, because sometimes we use zeros as placeholders. Sometimes when we're rounding numbers, we replace them with zeros to let us know it's an estimated number. So for instance, if I said, I went to a concert, and I think there was about 10,000 people there. Is that an exact number? No, I'm estimating. There's about 10,000. So that would not be an exact number, so that would only have a certain amount of significant digits. Okay? If I said I have 116 students, let's just round that to the tens place. What would I say then? 120. Okay? And so that would be an estimated number. It's not an exact number. I'm just estimating. I'm rounding, So, but if it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, always a significant number. Here's the problem. Your zeros become the problem. I'm going to go ahead and put all of these rules up so that I can write on the whole thing. Okay. Leading zeros are those numbers that are before a number. Okay. They are not significant. They're placeholders. Let me give you an example. If I had this number, okay, that only has 2 significant figures because these do not count. They are not significant. They are just there to be a placeholder to let you know that that's the place level. That's what the 10,000th place? Or tens, hundreds, yeah, 10,000 place. It's letting you know it's going there, okay? So their leading zeros are never, ever significant, okay? Captive zeros are ones that fall between 2 non-zero numbers, like this, 405. A captive zero is always significant because it's sandwiched. Sometimes they're called captive, sometimes they're called sandwiched, okay? They're always significant. They'll always count. So this would have 3 significant figures, okay? Trailing zeros are the ones at the end, okay? They only count if there's a decimal. Okay, so a while ago we said, went to a concert, 10,000 people there, right? That would only have, who wants to take a guess? How many significant figures would that have? 1. It would only have 1 significant figure. But let's say I'm at the concert and I'm that little person with the clicker, and every time somebody walks in, I click, 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 and I'm counting as you walk in, right? And I say, there was exactly 9,750 people at that concert. How many significant figures would that have? It would have 4 because that decimal means it's an exact. When I put the decimal, I'm saying it was exactly 9,750 people. So that would actually have 4 significant figures. It has to do with the decimal.
So when you record the answer, you have to put the.
I'm sorry, what?
So when you record your answer, like if it's.
So if I go into the lab and I measure on my balance and I say I'm giving the measurement of this the mass of this metal, and it comes out to 58.00 grams, I would write down 58.00 grams because that's an exact. I measured it exactly that. Okay. Yes.
How many significant figures would a number like 3.3 repeating have?
So in repeating, we don't do repeating, okay? We would look at, because you're going to get a repeating when you do a calculation, and there's going to be some rules about when we're calculating how to report it. So hold off for that just a second, okay? Because right now I just want to recognize if something's significant or not significant. Yes?
So you can put that decimal point there without it being followed by a zero?
Mm-hmm.
Okay.
Yes, because now if I did 97.5.000, oops, come back here. Oh, what happened? It just disappeared. I was writing and I hit the erase button on accident. Oops. Okay, sorry about that. So we're back at this one, the trailing. So let's say we had 975.00. How many significant figures would that have? 6.
Oh, really?
Once you have number, decimal, everything counts. Okay?
So if you had 10,000, and if you had 10,000 followed, and then you have the decimal after that, that would have 5 significant figures?
Like that?
Yes.
That would have 5.
Okay.
But without, 1.
Okay, thank you.
It's about the decimal. It's all about the decimal. Because when I put a decimal, I'm saying exact. Okay? Without the decimal, it's probably an estimation. Okay? And zeros are your issue. So I have this chart right here, and it kind of helps. And I leave it up. It's not up for the test. Okay? And if you're listening to the video, you just have to look at the chart in class. Okay? But this is a way to help you because it's about the zeros. The zero, you know. So we ask ourselves, does the number start with a 0? Okay? If the answer is no, you go over here. Then you start counting significant digits from the very first number because it's not starting with a 0. Okay? And then you go down here and you say, does the number have a decimal point? Yes. Then you say, continue counting until you get to the end of the number because there's a decimal place. But if it started with a non-zero number, started with a real number, and you go here and it doesn't have a decimal, you say no, you go over here. Does the number end in a 0? And if it's yes, you say stop counting significant digits when you reach the last non-zero number. Okay? But if it does not end in a 0, then you go to the end of the number. Does that make sense? Mm-hmm. So this will be up here so you can ask yourself these questions. If it starts with a 0, we say yes, then you start counting from the first non-zero number. So when we had that number like this, 0.0007889, okay? If we did that, we say, does it start with a 0? Yes. Start counting at the first non-zero number. So we don't start counting until we get to that 7. Okay? And then does it have a decimal point? Well, yes. And then you count to the end of the number. So that would have how many significant figures? 3. Okay? Yes?
So, like, what's the purpose of significant figures? Because obviously if you have a number, like, the one on the bottom, if, like, because the 3 zeros in front of it, like, change the... Oh.
This is blinding
I'm
me.
so sorry.
The 3 zeros, like...
They're placeholders.
Yeah, so, like, why are they not significant? Because if you don't...
Because I could also write this number like this, right?
Yeah. Okay. So...
They're placeholders. They're just letting you know that that value is in the tens, hundreds, 10,000s place.
Yes. But, like, the value of the number depends on those zeros, so
It's
why
not-
aren't they?
But they're placeholders. They're not significant. They're just,
Yeah.
it's just telling you that the value goes in that spot.
Right.
But it does not, they're not significant. It's not part of the measured value.
Okay.
Okay? And the purpose of them is we can never report our answers as more significant than what we measured. Because remember, our numbers in here are measurements. They're not just random numbers like in math class that they make up on their test. You know, they're actual measured numbers that you have to match the precision. Yes, ma'am.
I'm confused as to why when it's 0.00 something, it's only 3 or
Because
less.
these are placeholders. They're not part of the measured value, they're just placeholders.
So how come whenever
Okay, it's like if I say I only have, 5 cents to my name, how would I write 5 cents? As a decimal, I'd write 0.05, right? Okay, the 00 is not any value. It's just telling me I only have 5 cents. But if I did 50 cents, then I would not have that 0 there. Does that make sense? Okay. Okay. Now, if you're talking about, we're going to number 5 now. Okay. And it'll, as you practice this, it'll make more sense. I promise. Number 5 says exact numbers have an unlimited number of significant figures. If it's an exact number or exact conversion, we don't worry about it for significant figures. So, like example, 1.00 kilograms is equal to 2.205 pounds. That's exact. Someone measured that a long time ago, and that's exact. When we're talking about significant figures, we're talking about things that are estimated or measured, because there's always some uncertainty in measurements. Okay? And then if we're talking about scientific notation, we never look at this part. We just ignore that. That's never significant. We only look at what's written down before. Okay? Also, if you're putting a number into scientific notation, you have to include anything that's significant in that scientific notation. In other words, if I had this, let's put this number in scientific notation that we had up here. Since it's all significant, I would have to write 7.5000 times 10 to the third, because they're all significant.
Oh my.
But if I'm doing this number, I would do 1 times 10 to the 1, 2, 3, 4, because they're not significant. So if you're putting a number into scientific notation, you have to include everything that's significant in your scientific notation.
So if it says it's an exact number, we don't care about which digits are significant.
Correct. So we're going to be doing conversions a lot in here. You never use your conversion factors to determine your significant figures. You will always use your measured values. So typically you're going to use what's given to you in the problem. Okay? So like if they tell you I had 14.7 grams, you're going to use the 14.7 to get your sig figs for your answer. Yes, sir.
So would 10,000 with a decimal in scientific notation be 1.0000 times 10 to the fourth?
Absolutely.
Okay.
You got it. Okay. Now let's talk about the math rules. Okay. When you are, there's 2 sets of rules. One for multiplying and dividing, one for adding and subtracting. Okay. And if you've got both, the multiplying and dividing trump. They're the more important one. Okay. If you are multiplying and dividing the original data, you look at the data, and whichever has the fewest number of significant figures, you answer your answer in that. You match your answer to that. You round it. Okay? For example, if I was going to take 45 times 7,890, well, let's do 78,901. Everybody do that. And write down what the calculator gives you. Gives me a really big number. 3550. 3550,545. Is that what y'all got?
Yes.
Okay. But this has 2 significant figures. It's my smallest amount. So I have to match my answer to that. So how would I round that number to have 2 significant figures? These are my first 2 significant figures. Okay? So how would I round that number? What would my answer be?
3.6 times 10 to the. Would you put it in scientific notation?
I don't have to. I mean, yeah, I could because it's a big number. But for right now, let's just leave it normal.
36.
No, it would not just be 36.
36.000.
Oh,
Who's not a point?
There's not a point at all.
comma, zeros.
3,600,000.
You still need those zeros.
I know I was counting. That's how I would report that number. Because this 5 rounds that up, right? Why would it not just be 36? If it's 36, what did I just do to that value?
You just like
Totally. What if that was money I owed you? And I said, I'm just going to pay you in 2 significant figures. Here's $36. You'd be a little mad at me, wouldn't you? You cannot change the magnitude of the number by rounding. Okay? So just like in math, when you round, you replace with zeros. You don't just drop them off. Unless they're decimals. If they're decimals, you can drop them off, right? Okay? So you're always going to look at your fewest number of significant figures and match your answer to that when you're multiplying and dividing. Okay? When you are adding and subtracting, you don't care about the significant figures, you care about decimal places. Okay? So you will match your answer to match the number of decimal places. Okay? So let's say I'm adding up 45.0 whoops, 1 0 plus 33,000, let's use, I'm making up numbers as I go, 378.1511. Let's equal that. So what does that come out to be? I get that to be 423.2511.
Yes.
But I only have 2 decimal places here, so I would report that as 423.25. Notice I'm not looking at significant figures here. I'm looking at decimal places when I'm adding and subtracting.
Could you give us an example of like what would happen if you had both of those? You said
Oh, if you have both, like you're adding and multiplying,
right.
you go with you go with the multiplication rules. You look at your smallest number of sig figs.
So like what would be an example?
Like put it, star that one. That's the most important rule. It trumps the other one. If you have both operations at one time. Yes, sir.
Okay, if you see on the 45.10 and you see that it only has 2 decimal places, could you go to the 378 and take off the last 2, like take off the 1 1, and so it only has 1 decimal place, so you wouldn't have to
No.
the answer?
No.
No, okay.
Yeah, and I'll show you why. What if instead of 45.1, let's do that, plus we did 378.1578?
Oh, okay.
So then your answer would have been
26.
423.2578. Then your answer would be 423.26.
So you can't take the.
You still got to do the math. You round at the end. You never round in the problem, round at the end.
Okay.
Yeah. So that's why, that's a good question, actually. No one's ever asked that, but it is a good question. Don't drop it off because it might cause it to round up later. Okay? All right. So let's do some examples together. Okay. So we already talked about rounding. You know your rounding rules for math. If it's 5 or greater, you round up. If it's less than 5, you go down, or you just leave it alone. Anybody have any questions about that? Hopefully not. So this one, we're just going to count sig figs. So how many are in that first one? 6. And in case you haven't figured it out, SF stands for significant figures. It's very long to write out. Okay? And if ever on a test I say -1 SF, it's because you didn't have the right significant figures and I took a point off. Okay? How about number 2? How many are in that one? 2. Because those, we don't start counting until we get to the first real number, right? Or non-zero.
I thought SF was scale factor.
I don't know. For what?
Oh my god.
I don't have a scale factor in here, so I'm using it for significant figures. In chemistry, if it's SF, they're usually talking about significant figures. Number 3? 4. Number 4? 1. And number 5? 3. Because we don't care about this. We ignore it. Now, obviously, we care about it in the problem, but in terms of significant figures. Okay, now let's do some math. All right, that first one is 35.5. I typed in 34.5 and I just said it wrong. I'm on cold medicine, remember? Everything I do wrong today can be blamed on the fact that I'm sick, lack of oxygen to the brain, and I'm on cold medicine. I don't know what I'll use next week as my excuse, but that's what I'm sticking to this week. So I get 809. Oops. Forgot to say I was going to write. 809.37. How many significant figures do I need to report my answer to? 3 because of that one right there, right? So how would I record that?
809.
809.
Wait, wouldn't you need a point after that?
No.
No.
Don't tell. It's going to do it again. What is it about y'all's class? It started doing this yesterday in y'all's class.
Wait, why would you put a point after the 809?
Because it's not necessary. It's
If it was like 799.
you only really need to do that. It's not doing it on the recording. I don't know why it's doing it up there. So you only need to do that if it's a 0 to make it exact.
0. Okay.
It's already exact this way. 809 exact.
So
Okay, but
if,
oh wait.
if when you rounded it became like 800 or something, would you have to put a decimal? mix of those
To-
three.
yeah.
Okay.
And there are times when you have to put the number in scientific notation to get the right number of sig figs.
Okay.
Okay?
Can you put the decimal?
Nope, it's not necessary. It's redundant. Because that's already an exact number, 809. Because the 9, the last number, is a non-zero, so it's significant. So we know it's an exact number. Okay? 123 divided by 3.
41.
41. But how many significant figures do I need my answer in? So how would I record that? 40, yeah. That next number is 2.61 times 10 to the negative 1. It just got typed in funny, and it was making people get different answers because they were typing it in different. So what do you, I got 92.916. How many significant figures do I need my answer in? 3. So how would I record that?
92.9.
92.9.
Hey, that's the radio station in the country.
Okay, this next one is adding and subtracting. So do we care about significant figures? No, we just care about decimals. They both have 2 decimals. I should probably come up with a different example there, right? So it's just 67.64. The next one is subtraction.
Oh my, that's what it is.
That is a lot of decimals.
So for a question like number 5, you wouldn't take off some of the 8s.
No, why would you do that?
Okay. Gosh.
12.7 for that one? We
Yeah, so I need 1 decimal place, right? Because that only has 1. So 12.7 would be my answer.
Yeah, this is easy.
And then 6.35, 6 minus 3.45 works out to be 2.55. But I need no decimal places, so how would I report that number?
3.
I would say 3. Okay? I'm sorry it's doing that. It's not doing it on the recording, and I don't want to stop. But it did to y'all yesterday. It doesn't like y'all. Maybe it's on cold medicine. Yes, ma'am.
So what's the point of like having significant figures? Like what do you use
I cannot report my calculations to be more precise than my least precise measurement.
and why is
Because in my class in chemistry, any number that I'm recording is an indication of the precision of the measurement. Okay? And so if I wrote down an answer, the 4 decimal places, that would say to the person reading my results that I could get to four decimal places in my precision. And that's not the case. So your calculations cannot be more precise than your measurements. And it's with the advent of the calculator, because the calculator will give you a buttload of decimals. And if I was to write down this measurement as my answer, that's saying that I could get to that level of precision in my lab, and I can't. So it would be false. Yes.
Okay, but like if you see on question 6, your answer is like 0.45 off, which could mean
It depends on what, we're estimating. That's part of when we're doing calculations in the lab, and obviously our instrumentation in our lab is way less accurate and way less precise than at a university or a research lab.
okay.
So it's just, these are the rules that they came up with so that we're not saying that we're not capable of getting to that point.
But like if you see on number 6, the numbers is, I don't know, it's kind of like
Okay, number 6 is honestly there to give you an example of one without and one with decimals.
okay.
If we were in the lab and we were doing our balances, we would be in the same decimal places on most measurements.
Okay.
But it's there. Some of these are made up to give you examples of all the scenarios that could come up.
Okay, got it.
Okay.
So number 6 is kind of similar to something that wouldn't happen in a real lab.
It could.
Okay.
Depends on what we're adding and subtracting.
Okay.
Yeah. Don't make it too, you're going too deep. Okay. All right, let's talk about precision and accuracy now. Okay. And I will tell you this, these are the things on the test that people get backwards. Precision and accuracy. Magically it stopped. Okay. Precision is the closeness of a set of measurements. How much do they agree with each other? So if I had to go into the lab and I measured a piece of metal 3 times, how much do they agree with each other? Did I get the same number every time? Did I get slightly different every time? Okay? It's how well can I repeat a measurement, so repeatability. Okay? Accuracy is determined if the number is correct. How accurate am I? If the metal was 4.5 grams, did I get 4.5 grams or did I get 3.75? You know, how off was I basically? Okay? We're going to use throwing darts as an example. Okay? So I have this dartboard. I'm going to throw 3 darts. Are you ready? 1, 2, 3. We're slow today. So what kind of, would that be precise? Would that be accurate? Would it be both? Would it be neither?
Precise, but not accurate.
It is precise but not accurate because I'm hitting the same spot every time, but I'm just not hitting the accurate spot. Okay, so I'm precise there. Okay, next dartboard I throw. I am neither. I'm not precise nor accurate. Okay, and then the last dartboard, 1, 2, 3. I win. Yay! Okay. I am precise and I'm accurate, which is obviously what we like to be, okay? But it's not always the case, okay? With those measurements, there are 2 types of errors. There's random errors, which produce precision, and there's systematic errors, which are reducing your accuracy. So systematic error would be like my instrumentation. So like I can go in there, I have one balance back there that I have some like weights that I like check my balances, and there's one that's off by 0.5 gram. Can I still use that balance? Yes, because every time I weigh, it's off by 0.5 gram. And usually I'm using a balance to measure the difference in something, right? And so, now I don't use that bathroom. I don't want to say bathroom. I don't use that balance if I'm measuring to make up a solution because I know it's off by 0.5 gram. Okay, yes?
In the one where it was both in the middle, or all 3 were in the middle,
Mm-hmm.
it's not possible for it to be not precise in that one, would it be?
Oh, you're asking can you be accurate and not precise? Is that what you're asking?
Yes.
It's kind of hard to. So another thing is can I have precision of one measurement?
No.
No, because it's a repeatability of measurement. So, yeah, usually you can have precision without accuracy, but it's hard to have accuracy without precision because accuracy is a smaller value to obtain. Like I can get anywhere on the dartboard and I'm on the dartboard, but you want to be in the middle. So the only place you're accurate is in the middle.
So what if you made 2 in the middle and 1 like way off?
Well, then 2 of your measurements are precise, but the third one is an outlier. Yeah.
Wait, the 2 of the measurements are precise and accurate.
Yes, but that one is an outlier.
Okay, so
Yeah.
like on that third, the third, what do you call it?
Dartboard?
Yes, on the third dartboard, if one of them was in the middle, that means that a single measurement would have been accurate,
But not precise.
and then all 3 of them would not be precise.
Correct.
Okay, thank you.
Okay. Okay, so basically, in a nutshell, accurate means you're correct. Precise means you're consistent. So we have this set of data. It's supposed to be 6.00 meters long. We have 3 sets of data. Which set would be the most accurate?
Set Y.
Set Y. Also would be the most precise. The last thing you need to write down is this equation. You do need this equation. This is how we calculate percent error. Okay? On our lab Friday, you will be calculating percent error. Okay? Theoretical value is the accepted value. What is the known value? Okay? So I know what the density of these metals are that you are going to be measuring. Okay? That would be the theoretical value. The experimental value is what you get, your value. So when you go into the lab, whatever you calculate the density to be, it goes under experimental. And then you do this calculation to figure out what your percent error is. How close were you? Okay. Now, what do the big lines mean? What do these big lines mean? Absolute value, which means you cannot have a negative number.
Wait, couldn't you just do the opposite of, oh, never mind.